Hi students, for the past 2 weeks, you have learned about the principles of engineering economy analysis, the cost concepts, and the design economics. This week, I would like to talk to you about cost estimation techniques. The objective of this week is to present various methods for estimating important factors in an engineering economy study. Recall that you have learned about engineering economic procedure. Also, we have gone through several examples whereby different alternatives were developed for a given problem. What you have done is actually addressing step 1 and step 2 of the engineering economic procedure. Today, we address step 3, which is the development of the outcomes and cash flows for each alternative. Because engineering economic studies deal with outcomes that extend into the future, estimating the future cash flow for feasible alternatives is a critical step in the analysis procedures. Often the most difficult, expensive, and time-consuming part of an engineering economy study is the estimations of costs, revenues, useful lives, residual values, and other data pertaining to the alternatives being analyzed. A decision based on the analysis is economically sound only to the extent that these cost and revenue estimates are representative of what subsequently will occur. Whenever an engineering economic analysis is performed for a major capital investment, the cost estimating effort for the analysis should be an integral part of a comprehensive planning and design process. This process requires the active participation of not only the engineering designers, but also personnel from marketing, manufacturing, finance, and top management. Results of cost estimating are used for a variety of purposes, including setting selling price for quoting, bidding, or evaluating contracts, determining if a proposed product can be made and distributed at a profit, whereby price is equals to cost plus profit, evaluating how much capital can be justified for process changes and improvements, and setting benchmarks for productivity improvement programs. There are two fundamental approaches to cost estimating, the top-down approach and the bottom-up approach. Top-down approach uses historical data from similar projects to estimate cost, revenue, and etc. And this data was modified for changes in inflations or deflations, activity level, energy consumptions, size, weights, and other factors. This approach is best used early in the estimating process, when alternatives are still being developed and refined. Bottom-up approach, on the other hand, is more detailed. This approach breaks down a project into small manageable units and estimate their economic consequences. These smaller unit costs are added together with other types of costs to obtain an overall cost estimate. This approach usually works best when detail concerning the desired output, whether the product or service has been defined and clarified. Let us take a look at a simple example of cost estimating, which is to forecast the expenses of getting a Bachelor of Science from the university you are attending. In our solutions, we outline the two basic approaches just discussed for estimating this cost. Here shows how the top-down approach can be used to estimate the cost of a college degree. The top-down approach will take the published cost of a 4-year degree at the same or similar university and adjust it for inflations and extraordinary items that an incoming student might encounter, such as fraternity or sorority membership, scholarships, and tutoring. For example, suppose that the published cost of attending your university is $15,750 for the current year. This figure is anticipated to increase at a rate of 6% per year and includes full-time tuition and fees, university housing, and a weekly meal plan. Not included are the cost of books, supplies, and other personal expenses. For our initial estimate, these other expenses, including book supplies and other personnel expenses here, are assumed to remain constant at $5,000 per year. The total estimated cost for 4 years can now be computed and laid out in a table. Here we can see the cost estimated for each individual year. Tuition, fees, rooms, and boards are lumped together as the published cost, whereas other expenses include costs for book, supplies, and other personal expenses. To estimate the cost for year 1, we will need to adjust the published cost for the 6% annual inflation rate. By multiplying it with a factor of 1.06, and then we total up the adjusted published cost with other expenses, which is fixed at $5,000, to yield about $21,000 as the cost for year 1. Similar calculations is applied for the second, third, and fourth year, and this eventually gives us a total estimated cost of about $93,000 for a 4 years Bachelor of Science degree. You have seen the top-down approach, which is quite a crude estimate of the cost. Bottom-up approach is a more detailed approach. This approach will first break down anticipated expenses into different categories for each of the 4 years at the university. For example, we can break down the cost into tuition and fee, books and supplies, living expenses, and transportations. Underneath each of these categories, we can have further details of the different costs. Tuition and fee can be estimated fairly accurately in each year, as can books and supplies. Suppose that the average cost of a college textbook is $100. You can estimate your annual textbook cost by simply multiplying the average cost per book by the number of courses you plan to take. The other two categories, like the living expenses and transportations, are probably more dependent on one's lifestyle. Whether you own and operate a car and living in a high-end condo off campus can dramatically affect the estimated expenses during the college years. The integrated cost estimation approach has three basic components, including work breakdown structure, cost and revenue structures, and estimating techniques. In work breakdown structures, we define as successive levels of detail the work elements of a project and their interrelationship. Cost and revenue structures involves classifications or delineations of cost and revenue categories to estimate the cash flows at each level of work breakdown structure. And for estimating techniques, we select mathematical models to estimate the future costs and revenues during the analysis period. Here shows the flowchart of the integrated approach. These three basic components, together with integrating procedure steps here, provide an organized approach for developing the cash flows for the alternatives. The integrated approach starts with a description of a project in terms of the work breakdown structures. Work breakdown structures is used to describe the project and the unique characteristic of each alternative in terms of design, the material requirements, labor, and etc. Then these variations in design, resource requirements, and other characteristics are reflected in the future costs and revenues, and therefore in the net cash flows for that alternative. To estimate future costs and revenues for an alternative, the perspective or viewpoint of the cash flows must be established, and the estimating baseline and analysis period should be defined. Normally, cash flows are developed from the owner's viewpoint. The net cash flows for an alternative represent what is estimated to happen to future revenues and costs from the perspective being used. Therefore, the estimated changes in revenues and costs associated with an alternative have to be relative to a baseline that is consistently used for all alternatives being compared. So in this chart, we can see that we iterate the process over all feasible project alternatives using work breakdown structure. The first basic component in an integrated approach to developing cash flows is the work breakdown structure. The work breakdown structures is a basic tool in project management and engineering economy study. It serves as a framework for defining all project work elements and their interrelationships, collecting and organizing information, developing relevant cost and revenue data, and management activities. Each level of a work breakdown structure divides the work elements into increasing details. This is a diagram of a typical four-level work breakdown structure. It is developed using a top-down approach in successive levels of detail. The project is divided into its major work elements at level 2. And these major work elements are then divided to develop level 3 and so on. For example, an automobile at the first level of the work breakdown structure can be divided into second-level work elements such as the chassis, drivetrain, and the electrical system. Then each second-level elements can be subdivided further into third-level elements. The drivetrain, for example, can be subdivided into engine and transmission. This process is continued until the desired details in the definitions and descriptions of the project or system is achieved. Different numbering schemes may be used. The objective of the numbering scheme are to indicate the interrelationship of the work elements in the hierarchy. The scheme illustrated here is an alphanumeric format. A work breakdown structure has other characteristics. For example, both functional and physical work elements are included. Examples of functional work elements are logistical support, project management, marketing, engineering, and system integrations. And physical work elements, on the other hand, are the parts that make up a structure, product, piece of equipment, or similar item. They require labor, materials, and other resources to produce or construct. The content and resource requirements for a work element are the sum of the activities and resources of related sub-elements below it. A project work breakdown structures usually includes recurring and non-recurring work elements. Example of recurring work elements is maintenance, and example of non-recurring work elements is the initial construction. This is one example on a work breakdown structures for a construction project. You have been appointed by your company to manage a project involving constructions of a small commercial building with 2 floors of 15,000 gross square feet each. The ground floor is planned for small retail shops and the second floor is planned for offices. Develop the first 3 levels of a representative work breakdown structures adequate for all project efforts from the time the decision was made to proceed with the design and constructions of the building until initial occupancy is completed. Bear in mind that there will be variations in the work breakdown structures developed by different individuals for commercial building. A representative 3-level work breakdown structure is shown here. The level 1 is the total project, which is the commercial building project. At level 2, the project is divided into 7 major physical work elements and 3 major functional work elements. Example of physical work elements include site work and foundations, exterior, interior, roof, electrical system, mechanical system, and real estate. The functional work elements here include project management, architecture or engineering service, and sales. Then each of these major elements is divided into sub-elements as required at level 3. For example, the exterior elements is subdivided into framing, siding, windows, entrances, and installations. The numbering scheme used in this example is all numeric. The second basic component of the integrated approach for developing cash flows is the cost and revenue structure. This structure is used to identify and categorize the costs and revenues that needs to be included in the analysis. The life cycle concept and work breakdown structures are important aids in developing the cost and revenue structures for a project. And the life cycle defines the maximum time period of the project. It establishes a range of cost and revenue elements that need to be considered in developing cash flows. The work breakdown structures focuses the analyst's effort on the specific functional and physical work elements and on their related costs and revenues. Perhaps the most serious source of errors in developing cash flows is overlooking important categories of costs and revenues. The cost and revenue structure, normally prepared in tabular or checklist form, is a good means of preventing such oversights. Technical familiarity with the project is essential in ensuring the completeness of the structure, as are using the life cycle concept and the work breakdown structures in its preparation. Here is a brief listing of some categories of costs and revenues that are typically needed in an engineering economy study. These include capital investment, labor cost, material cost, maintenance cost, property taxes and insurance, overhead cost, disposal cost, revenue spent on sales, quality and scrap cost, and the market or salvage values. Capital investment can be divided into two types, the fixed and working capital investment. Fixed capital is the investment done by the business for accruing long-term benefits. A fixed capital investment can be tangible asset such as building or intangible asset such as intellectual property. The fixed capital is not at all liquid and it cannot be converted into cash or kind immediately. The working capital, on the other hand, is the daily requirement or investment pumped into the business. It is used to acquire assets of the company and include cash, inventory, accounts receivable, account payable, and the portions of debt due within 1 year. Working capital is very much liquid and can be converted into cash or kind immediately. The third basic component of the integrated approach involves estimating techniques or models. These techniques, together with the detailed cost and revenue data, are used to develop individual cash flows estimates and the overall net cash flows for each alternative. Remember, the purpose of estimating is to develop cash flow projections, not to produce exact data about the future, which is virtually impossible. Neither a preliminary estimate nor a final estimate is expected to be exact. Rather, it should be adequately suit the need at a reasonable cost and is often presented as a range of numbers. Cost and revenue estimates can be classified according to the detail, accuracy, and the intended use as follows. Order of magnitude estimates are used in the planning and initial evaluation stage of a project. It is used in selecting the feasible alternatives for the study. They typically provide accuracy in the range of ±30% and are developed through semi-formal means such as conferences, questionnaires, and generalized equations applied at the level 2 or level 1 of the work breakdown structures. Semi-detailed or budget estimates are used in the preliminary or conceptual design stage of a project. Semi-detailed estimates are compiled to support the preliminary design effort and decision-making. The accuracy usually lies in the range of ±15%. Estimating equations applied at level 3 and level 2 of the work breakdown structures are normally used. Definitive or detailed estimates are used as the basis for bids and to make detailed design decisions. The accuracy is ±5%. They are much more from specifications, drawings, site surveys, vendor quotations, and in-house historical records, and are usually done at level 3 and successive levels in the work breakdown structure. Thus, it is apparent that a cost or revenue estimate can vary from the back-of-the-envelope calculations by experts to very detailed and accurate predictions of the future prepared by a project team. The level of detail and accuracy of estimate should depend on the following: time and effort available as justified by the importance of the study, difficulty of estimating the items in question, methods or techniques employed, qualifications of the estimators, and sensitivity of study results to particular factor estimates. The general relationship of the level of details, the accuracy of the estimates, and the cost of performing the estimates is shown here. As estimates become more and more detailed and more accurate in these directions, the cost of performing the estimates increases dramatically. This illustrates the idea that cost and revenue estimates should be prepared with full recognition of how accurate a particular study requires them to be. A variety of sources exist for cost and revenue estimations. These include the accounting records, which consist of a detailed records of monetary transactions between established categories of assets. Accounting records are a good source of historical data, but have some limitations when used in making prospective estimates for engineering economic analysis. It is because the records rarely contain direct statements of incremental cost or opportunity cost, both of which are essential in most engineering economic analysis. Other sources within the firm. The typical firm has a number of people and functions that may be excellent sources of estimating information. Examples of functions within firms that keep records useful to economic analysis are engineering, sales, productions, quality, purchasing, and personnel. Sources outside the firm. There are numerous sources. The main problem is in determining those that are most beneficial for particular needs. Some commonly used outside sources include published information and personal contacts. Published data include technical directories, government publications, industry surveys, and trade journals. Personal contacts include vendors, salespersons, customers, bank, government agencies are often willing to provide information on the basis of a serious and tactful request. Research and development. If the information is not published and cannot be obtained by consulting someone, the only alternative may be to undertake R&D to generate it. Classic examples are developing a pilot plant and undertaking a test market program. We are going to have a look at a number of models that are applicable for order of magnitude estimates and for many semi-detailed or budget estimates. These models are useful in the initial selections of feasible alternatives for further analysis and in the conceptual or preliminary design phase of a project. Sometimes they even can be used in the detailed design phase of a project. These models are indexes, unit technique, and factor technique. Now we take a look at indexes. What is an index? An index is a dimensionless number that indicates how a cost or price has changed with time with respect to a base year. Indexes provide a convenient means for developing present and future cost and price estimates from historical data. This historical data is obtained from the base year. An estimate of the cost or selling price of an item in year N can be obtained by multiplying the cost or price of the item at an earlier point in time, for example in year K, by the ratio of the index value in year N to the index value in year K. This is sometimes referred to as the ratio technique of updating costs and prices. Use of this technique allows the cost or potential selling price of an item to be taken from historical data with a specified base year and updated with an index. This concept can be applied at the lower levels of a work breakdown structure to estimate the cost of equipment, materials, and labor, as well as at the top level of a work breakdown structure to estimate the total project cost of a new facility, bridge, and so on. Okay, this is an example on the use of this index formula to calculate cost. Indexing the cost of a new boiler. A certain index for the cost of purchasing and installing utility boilers is key to 1988, where its baseline value was arbitrarily set at 100. Company XYZ installed a £50,000 per hour boiler for $525,000 in year 2000, when the index had a value of 468. This same company must install another boiler of the same size in year 2014. The index in 2014 is 542. What is the approximate cost of the new boiler? Okay, here we are requested to estimate the cost of the boiler in year 2014 by referring to the price of the boiler in earlier point in time. Okay, we use year 2000 as our reference year rather than 1988 since only the price of the boiler in year 2000 is given. Okay, therefore, N is equals to 2014 and K is equals to 2000. And we can approximate the cost of the boiler in 2014 by using this formula. Okay, see, 2000 is equals to $525,000, whereas the index in year 2000 is equals to 468 and the index in year 2014 is 542. By substituting these values into the formula, we get the cost of the boiler in year 2014 equals to $608,013. Indexes can be created for a single item or for multiple items. For multiple items, we use composite index. Composite index is created by averaging the ratios of selected item costs in a particular year to the cost of the same item in the reference year. Here shows the formula to calculate the composite index. As shown by this formula, we can assign different weights W1 until Wm to the items according to their contributions to the total cost. These weights from W1 to Wm here can sum to any positive number, but typically sum to 1 or 100. Almost any combinations of labor, materials, products, services, and so on can be used for a composite cost or price index. And this CNM and CKM here refers to the unit cost or price of the M item in year N and year K. Again, year K is our reference year. This is an example showing how a composite index or weighted index is calculated. Weighted index for gasoline cost. Based on the following data, develop a weighted index for the price of a gallon of gasoline in 2014, where 1996 is the reference year having an index value of 99.2. The weight placed on regular unleaded gasoline is 3 times that of either premium or unleaded plus, because roughly 3 times as much regular unleaded is sold compared with premium or unleaded plus. This table here shows the 3 different types of gasoline and their price in 1996, 2010, and 2014. We can use this formula to calculate the composite index. Here shows the weights given to the different types of gasoline. Our reference year K is equals to 1996, and this is the year when the index is calculated. And we denote it as N equals to 2014. Cn is the price of the gasoline in year 2014 and Ck is the price of gasoline in year 1996. Let's say 1 is the premium gasoline. Okay, the ratio of CN1 to CK1 is therefore 315 divided by 114. Okay, if 2 refers to the unleaded class, then the ratio of CN2 to CK2 would be 305 divided by 103, and so on. Okay, IK here is the index value for 1996, which is 99.2. Okay, by substituting these values in this formula, we will get the composite index in 2014 as shown in the next slide. So the composite index in year 2014 is equals to 296. Now, if the index in 2016, for example, is estimated to be 327, can we determine the corresponding 2016 prices of gasoline from the composite index? We can determine the price of the different types of gasoline in 2016 by using this index formula. We can rewrite it this way, replacing the symbol N and K with year. And now the reference year is 2014 with the index of 296, whereas the year in which the price is to be determined is 2016 with index of 327. Okay, see 2016 here is the price of gasoline in 2016, and the price for different types of gasoline are listed here. Okay, by substituting the values into the formula, you will get the price of the premium gasoline in 2016 equals to 348 cents per gallon, unleaded plus equals to 337 cents per gallon, and the regular unleaded equals to 315 cents per gallon. Here is a question for you to try on your own. In 2002, Acme Chemicals purchased a large pump for $112,000. Acme keys in their cost estimating for this pump to the industrial pump index with a baseline of 100 established in 1992. The index in 2002 was 212. Acme is now in year 2010 considering constructions of a new additions and must estimate the cost of the same type and size of pump. If the industrial pump index is currently 286, what is the estimated cost of the new pump? Please try this question on your own and we shall discuss the answer in our next class. We have seen the index technique. Now we'll look at the second technique known as unit technique. The unit technique is widely used, known, and understood. It involves the use of per unit factor along with the appropriate number of units to find the total estimate of cost. An often used example is the cost of a particular house. Using a per unit factor says $120 per square foot and applying that to a house with 3,000 square feet results in an estimated cost of $360,000. Other examples of unit factors include capital cost of plant per kilowatt of capacity, revenue per customer served, and construction cost per square foot. And this is another pose and solve questions. Suppose the Air Force B-2 aircraft costs $68,000 per hour to own, operate, and maintain. A certain mission requires two B-2 aircraft to fly a total round-trip time of 45 hours. What is the total cost of this mission? Okay, again, please try this question on your own and we will discuss next week. The third and the last estimating technique we look at is factor technique. The factor technique is an extension of the unit technique, where the product of several quantities are summed and then added to components estimated directly. Here is the formula for factor technique, which consists of two parts. The first part is the summations of the component that can be estimated directly. The number of components is given by D. The second part is the formula for unit technique. Here we use M to represent the number of components that is estimated using the unit technique. The cost of each component is estimated from the product of F and U, F is the cost per unit of the component, and U is the number of units of the component. Okay, the M components were summed together before added to the first part of the formula. Here is an example on the use of vector technique. Okay, suppose that we need a slightly refined estimate of the cost of a house consisting of 2,000 square feet, 2 porches and a garage. Using a unit factor of $85 per square foot, $10,000 per porch, and $8,000 per garage for the two directly estimated components, calculate the total estimated cost. For the solutions, we can make use of this formula. It was stated clearly that there are two directly estimated components, which are the 2 porches and 1 garage. We can be used to fill this part of the formula. The component which is estimated using the unit technique is the price of the house, which is estimated using the second part of this formula. Here shows the formula after inserting with the values. The 2 times $10,000 here is the price for the 2 porches, and $8,000 here is the price for the single garage, and $85 per square foot multiplied with 2,000 square feet gives the price of the house. In total, the cost is $198,000. This is another example. Analysis of building space cost estimates. The detailed design of the commercial building affects the utilizations of the gross square feet, and thus the net rentable space available on each floor. Also, the size and locations of the parking lot and the prime road frontage available along the property may offer some additional revenue sources. As project manager, analyze the potential revenue impacts of the following considerations. The first floor of the building has 15,000 gross square feet of retail space, and the second floor has the same amount planned for office use. Based on discussions with the sales staff, develop the following additional information. A. The detailed space should be designed for 2 different uses. 60% for restaurant operations with utilizations of 79% and yearly rent of $23 per square foot, and 40% for retail clothing store with utilizations of 83% and yearly rent of $18 per square foot. B. There is a high probability that all the office space on the second floor will be leased to one client with utilizations of 89% and yearly rent of $14 per square foot. C. An estimated 20 parking spaces can be rented on a long-term basis to 2 existing businesses that adjoin the property. Also, 1 spot along the road frontage can be leased to a sign company for erections of a billboard without impairing the primary use of the property. In this example, we need to calculate the annual project revenue given the information how each part of the buildings can be used to generate revenue. The utilization here means the ratio of rentable space to gross square feet. And the rent per month per parking space is $22, and the rent per month per billboard is $65. Based on these information, we can estimate the annual project revenue by using this formula. This is actually a formula for vector technique. The first part here consists of the revenues that can be directly estimated, which include the parking spaces and billboards. The second part is the revenue to be estimated using the unit technique, which is the rent. The revenue generated from the parking space can be estimated by multiplying the 20 parking spaces with the rent per month per parking space of $22 and 12 months of a year. The revenue generated from the billboard can be estimated by multiplying one billboard with the rate per month per billboard of $65 and 12 months of a year. The rent is estimated from this unit formula. SJ is the space in gross square feet being used for purpose J. UJ is the space J utilization factor in percent net rentable. And DJ is the rent per rentable square foot per year of building space used for purpose J. From the text, we can assign J equals to 1 for retail space at first floor, which is intended for restaurant purpose. J equals to 2 for retail space at first floor, which is used for retail clothing store. And J equals to 3 for office space at the second floor. Here shows the formula after we have substituted the symbol with their values. This is the revenue from the parking space, billboard, restaurant, clothing store, and the office. The first number of each of these terms here refers to the space being used. Restaurant occupies 9,000 square feet, which is 60% of the total retail space at first floor. A clothing store occupies 6,000 square feet, which is 40% of the total retail space at first floor, whereas office occupies the entire second floor, which is 15,000 square feet. The second number here refers to the percent utilization, which is the ratio of rentable space to gross square feet. The third number is the yearly rent per square foot of the respective space. Overall, the annual revenue from this calculation yields $446,130. A breakdown of the annual estimated project revenue shows that 1.4% is from miscellaneous revenue sources, whereas 98.6% is from leased building space. From a detailed design perspective, changes in annual project revenue due to changes in building space utilization factors can be easily calculated. For example, we can calculate the changes to the total revenue if the ratio of rentable space to gross square feet improves by 1%. Here shows the solution. Here we just add the 1% changes in rentable space to the unit formula. Then the total summations of the rent here is minus from the difference between the total annual project revenue and the miscellaneous cost from parking space and billboard. This difference here gives us the original rent before the 1% changes. So the total change in annual revenue is equals to $5,250 per year due to the improvement of the rentable space by 1%. Now we'll proceed to parametric cost estimating. Parametric cost estimating involves the use of historical cost data and statistical techniques such as linear regressions to predict future cost. Statistical techniques is used to develop cost estimating relationships that ties the cost or price of an item, for example, the product, good, service, or activity, to one or more independent variables, which is known as the cost drivers. Cost drivers are design variables that account for a large portion of total cost behavior. These models are used in the early design stages to get an idea of how much the product or project will cost on the basis of a few physical attributes such as weight, volume, and power. The output of the parametric models is used to gauge the impact of design decisions on the total cost. Here lists a variety of products and the associated cost drivers. For example, the cost drivers for reciprocating engine is the piston displacement, compression ratio, and the horsepower, whereas the cost driver for electrical power plants is kilowatt. Various statistical and mathematical techniques are used to develop the cost estimating relationship. Okay, we'll look at two commonly used techniques for estimating relationship, including power sizing technique and the learning curve. Power sizing technique, which is also known as exponential model, is frequently used for developing capital investment estimates for industrial plants and equipment. This cost estimating relationship recognizes that cost varies as some power of the change in capacity or size as given by this formula. CA and CB correspond to the cost for plant A and plant B respectively. Both are in dollars as of the point in time for which the estimate is desired. SA and SB correspond to the size of plant A and plant B respectively, and they are both in the same physical unit. X is the cost capacity factor to reflect economies of scale. The value of this cost capacity factor will depend on the type of plant or equipment being estimated. For example, X is equals to 0.68 for nuclear generating plants, and it takes a value of 0.79 for fossil fuel generating plants. Okay, X less than 1 indicates decreasing economies of scale, which means each additional unit of capacity costs less than the previous unit. S greater than 1 indicates increasing economies of scale, which means each additional unit of capacity costs more than the previous unit. And X equals to 1 indicates a linear cost relationship with size. This is an example on power sizing models for cost estimating. Suppose that an aircraft manufacturer desires to make a preliminary estimate of the cost of building a 600 megawatt fossil fuel plant for the assembly of its new long-distance aircraft. It is known that a 200 megawatt plant cost $100 million 20 years ago, when the approximate cost index was 400 and that cost index is now 1,200. The cost capacity factor for a fossil fuel power plant is 0.79. This question is asking us to estimate the cost of building a 600 megawatt plant. And we can estimate this by using this power sizing model or formula. Before using the power sizing model to estimate the cost of 600 megawatt plant, which corresponds to CA here, we must first use the cost index information to update the non-cost of 200 megawatt plant 20 years ago to current cost to get CB here. The current cost of a 200 megawatt plant can be estimated using this index formula. The cost index is 1,200 in current year, and it was 420 years ago. The cost of the plant 20 years ago was $100 million. With these informations, we obtain CB equals to $300 million. Next, we can obtain the following estimate for the 600 megawatt plant with reference to the cost of 200 megawatt plant, which cost $300 million. Here we insert the cost capacity factor for the power plant equals to 0.79. With these informations, we obtain the estimated cost to be $714 million for building this 600 megawatt plant. This is another pause and solve questions. Acme Logistics provides less than truckload or LTL services throughout the US. They have several hubs where they use cross-docking to move goods from one trailer to another. Acme built its last hub 10 years ago and it had 36 dock doors. The cost index at that time was 140 and the total cost was $6 million. Acme plans for a new hub that will have 48 dock doors. The cost index now is 195. Acme will use a capacity factor of 0.82. What is the estimated cost of the new hub? I would like you to try these questions on your own and we can have a discussions on the answer next week. Now let's take a look at the second parametric cost estimating technique known as learning curve. A learning curve is a mathematical model that explains the phenomenon of increased worker efficiency and improved organizational performance with repetitive productions of a goods or service. The learning curve is sometimes called an experience curve or a manufacturing progress function. Fundamentally, it is an estimating relationship. The learning curve effect was first observed in the aircraft and aerospace industries with respect to labor hours per unit. However, it applies in many different situations. For example, the learning curve effect can be used in estimating the professional hours expended by an engineering staff to accomplish successive detailed designs within a family of products, as well as in estimating the labor hours required to assemble automobiles. The concept of learning curve is that as the number of units produced increases, some input resources decrease on a per output unit basis. Examples of input resources are energy cost, labor hours, material cost, and the engineering hours. Most learning curve assumes a constant percentage reduction occurs as the number of units produced is doubled. For example, if 100 labor hours are required to produce the first output unit and a 90% learning curve is assumed, then 90 labor hours will be required to produce the second output unit, and this is obtained by multiplying 100 labor hours with 0.9, which corresponds to the 90% learning curve. Similarly, 81 labor hours will be required to produce the fourth output unit, and 72.9 labor hours will be required to produce the eighth output unit, and so on. And the number of labor hours here were obtained by multiplying the labor hours of the previous output unit with 0.9. And therefore, we can see that a 90% learning curve results in a 10% reduction in the labor hours each time the production quantity is doubled. And these equations can be used to compute resource requirements, assuming a constant percentage reduction in input resources each time the output quantity is doubled. U is the output unit number, and ZU is the number of input units needed to produce the output unit U. K is the number of input units needed to produce the first output unit, and N is the learning curve exponent, which is equals to the ratio of log x to log 2, whereby S is the learning curve's log parameter as a decimal. And the total input units, for example, time, Tx required to produce x unit is given by these equations, which is the cumulative sum of the number of input units needed to produce each output unit U. And for example, to calculate the total labor hours for the productions of 4 units of outputs, we can sum up the labor hours for the productions of the first, second, third, and the fourth unit of output. Let's take a look at one example. Assume the first unit of productions required 3 hours for assembly. The learning rate is 75%. Find A, the time to assemble the 8th unit, and B, the time needed to assemble the first 6 units. Here is the solutions. To calculate the time to assemble the 8th unit, we can use this formula. U here stands for the number of output units to estimate the assembly time, which is 8. K is the time for the productions of the first unit, which is 3 hours. And N here is given by the ratio of log S to log 2, whereby S is the learning rate in decimal, which is 0.75. And with these informations, the estimated time to assemble the 8th unit is equals to 1.27 hours. To estimate the time needed to assemble the first 6 units, we can use this second equation. Okay, in these equations, the time needed to assemble the first 6 units is equal to the cumulative sum of the time required to assemble the first unit to the 6th unit. By substituting all values into the formula, we will get the total time to assemble the first 6 units equals to 11.8 hours. Okay, this is a second example on learning curve. A learning curve for a Formula Car design team. The mechanical engineering department has a student team that is designing a Formula Car for national competition. The time required for the team to assemble the first car is 100 hours. The improvement or learning rate is 0.8, which means that as the output is double, the time to assemble a car is reduced by 20%. Use these information to determine A. The time it will take the team to assemble the 10th car. B. The total time required to assemble the first 10 cars. And C. The estimated cumulative average assembly time for the first 10 cars. Solve by hand and by spreadsheet. Here shows the solutions by hand. For the solutions to question A, assuming a proportional decrease in assembly time for output units between double quantities, we have the time it takes for the team to assemble the 10th car to be estimated using this formula. KU is equals to 10, which is the number of output units where the assembly time is to be estimated. K is the time to assemble the first car, which is 100 hours, and the learning rate is 0.8. And with these values, the estimated time to assemble the 10th car would be 47.6 hours. Okay, for solutions to question B, the total time to produce 10 units of car can be estimated using these equations, which cumulatively sum up the time needed to produce the first car up to the 10th car. And from these calculations, the total time would be 631 hours for producing 10 cars. Okay, for solution C, the cumulative average time for 10 units of car is given by the total time to produce 10 cars divided by 10, which is equal to 63.1 hours for each car. Here shows the spreadsheet solutions. Cell B1 is used to store K, which is the time needed to assemble the first unit of car. Cell B2 is storing S, which is the learning rate, and cell B4 is storing the ratio of log S to log 2. For each unit number, unit time to complete the assembly, the cumulative total time, and the cumulative average time are computed with the use of equations shown on top respectively. And this is the plot of unit time and cumulative average time. As we can see, the unit time and cumulative average time decreases when the number of output units increases. And this spreadsheet model can be used to examine the impact of different learning slot parameters on predicted car assembly times by changing the value of cell B2. For example, we can try 90% learning rate, 70% learning rate, and so on. Now we take a look at the last sections of this topic, estimating a cost estimating relationship or CER. A cost estimating relationship is a mathematical model that describes the cost of a project as a function of design variables. CERs are useful tools because they allow the estimator to develop a cost estimate quickly and easily. Furthermore, estimates can be made early in the design process before detailed information is available. As a result, engineers can use CERs to make early design decisions that are cost-effective in addition to meeting technical requirements. There are 4 basic steps in developing a CER. These include problem definitions, which is normally involve developing work breakdown structures to describe the elements of the problem. A review of the completed work breakdown structures can help to identify potential cost drivers for the development of CERs. Second, data collections and normalizations is the most critical step in the development of a CER. The work breakdown structures is also useful in the data collection phase by organizing the data and ensure that no elements are overlooked. Data can be obtained from both internal and external sources. Costs of similar projects in the past are one source of data. Published cost information is another source of data. Once collected, data must be normalized to account for differences due to inflation, geographical locations, labor rates, and so on. The third step is CER equations development. It involves one to formulate an equation that accurately captures the relationship between the selected cost drivers and project costs. And the final step is to validate the model and perform documentations. Here list 4 general equations types commonly used in CER development. In these equations, B0, B1, B2, and B3 here are the constants, while x1, x2, x3, and etc. represents the design variables. A simple yet very effective way to determine an appropriate equation form for the CER is to plot the data. If a plot of the data on regular graph paper appears to follow a straight line, then a linear relationship is suggested. If a curve is suggested, then try plot the data on semi-log or log-log paper. If a straight line results on semi-log paper, then the relationship is logarithmic or exponential. If a straight line results on log-log paper, then the relationship is power curve. Once we have determined the basic equation form for the CER, the next step is to determine the values of the coefficients in the CER equations. This corresponds to B0, B1, B2 values. The most common technique used to solve for the coefficients value is the method of least squares. Basically, this method seeks to determine a straight line through the data that minimizes the total deviations of the actual data from the predicted data values. The line itself represents the CER. In other words, we can do curve fitting to our data to find out the line that represents the CER. This example shows how to determine the cost estimating relationship or CER for the spacecraft. In the early stages of design, it is believed that the cost of a Martian rover spacecraft is related to its weight. Cost and weight data for 6 spacecraft have been collected and normalized and are shown in this table. A plot of the data suggested a linear relationship. Use a spreadsheet model to determine the values of the coefficients for the CER. Here shows the solutions which is carried out using basic regression features of Excel. First, you can paste the data into the Excel spreadsheet as shown here. Then call out this regression dialog box using the data analysis regression menu command. For older versions of Excel, you can find the regression options under the tool menu. To perform regressions or line fitting, you only need to enter the cost and weight data for the spacecraft in this dialog box and let the Excel find the regression coefficients automatically for us. The input Y range here is entered with the cost data, whereas the input X range is entered with the weight data. The challenge in spreadsheet regressions lies in making sure that the underlying regression assumptions are satisfied and the output is interpreted properly. The result of the analysis, including the regression statistic, ANOVA, and the coefficients, are generated by Excel and are displayed beginning in cell A9, and this is specified in the dialog box in this output range. Also, here we tick the box for line fit plots so that the plot of data and the fitted line will be displayed. The coefficients B0 and B1 can be found in cells B25 and B26 respectively for the CER. With these informations, the resulting CER relating spacecraft cost in millions of dollars to spacecraft weight is given by these linear equations. And this is the B0 and this is the B1. X represents the weight of the spacecraft in pounds, and X has a value between 400 and 1,200. The final step in developing CER is model validations and documentations. Once CER has been developed as shown in previous example, we need to determine how well the CER can predict cost for model validations and document the use of CER. Validations can be accomplished with statistical goodness of fit measures such as standard errors and correlation coefficient. Analysts must use goodness of fit measures to infer how well the CER predicts cost as a function of the selected cost drivers. The standard error measures the average amount by which the actual cost value and the predicted cost values vary, whereas correlation coefficients measures the closeness of the actual data points to the regression line. We can determine these two values from the output of the regressions model. For previous example, standard error can be found in cell B15, whereas the correlation coefficients can be found in cell B12. The value of the correlation coefficient is close to 1, indicating a strong positive linear relationship between the cost of spacecraft and spacecraft weight. Here comes the end of today's topic. Thanks for listening. I have prepared some tutorials for you to try at home and we can discuss next week. See you, bye bye.